This is a bacteria growth application problem. I'm going to use this problem to introduce what exponential growth is in application. Let's read the problem first. After 2 hours, there are 100 bacteria in a culture. And after 6 hours, there are 500 bacteria in that culture. So it looks like the number of bacteria is increasing. Suppose the number of bacteria follows exponential growth. How many bacteria will be in the culture after 9 hours? So this one we have to do a lot of setup. So majority of the works, the algebra, they are all in setting up the exponential model. So what is exponential model? There you have it. The exponential model is y equals to a times e to the kt. Some textbook use some other letters, but I always use y equals to a times e to the kt. A is the initial population, the number in front of the e that represent initial population, and then t is the time, k is the rate. When k is positive, there is an exponential growth. K is negative, there is an exponential decay. You cannot have k equals to 0 because once k equals to 0, e to the 0 is just equals to 1, so the exponential term is gone. And then, oh, this is a duplicate, t is equals to time, and then the graph of the exponential model looks like that. I do not have any curve on the left hand side of the y-axis because t cannot be negative, right? When t represents time, time cannot be negative. So that's why compared to the graph of the exponential function e to the x, I cannot put any curve on the left hand side of the y-axis. Okay, do you see this? I said find the rate and the initial population first. I gave you 2 hours, 100 bacteria, 6 hours, 500 bacteria. I didn't give you how many bacteria are there initially. So that means when time is equals to 0 at the very beginning, how many bacteria are in the culture? I didn't give you that. I want you to find out. So we have to do a lot of work to find out. So first of all, I gave you time equals to 2, and then the population is 100, right? And then when time is equals to 6, the population is 500. Okay, so let's plug in what we have. So we have 100 population. The initial population is don't know, so that is an a e to the kt. We don't know what k is. T is equals to 2. Let's solve for a. So in this problem, a is equals to 100 divided by e to the 2k. So that is the initial population in terms of k. And then how about the t equals to 6? So we have 500 equals to the initial population e to the kt. So k is equals to k, and then t is equals to 6. So what we are going to do next is we are going to plug in the a right over there. We are going to do a plug-in. So we have 500 equals to 100 divided by e to the 2k, and then times e to the 6k. Can you simplify that? E to the 6k divided by e to the 2k, 6 minus 2 is equals to 4. So we have 500 equals to 100 times e to the 4k. Now, this is one equation with one variable, and then let's solve for k. We divide both sides by 100, so we have 5 equals to e to the 4k. And then how do you bring the k down? So to bring the k down, we have to take the natural log on both sides to bring the k down. And then what do you get next? You have ln phi equals to 4k, right? Because ln e is equals to 1. So let's bring it over here. So we have ln phi equals to 4k times ln e. Ln e is equals to 1. So we have ln phi equals to 4k. And then k is equals to ln phi divided by 4. And then if you evaluate that, this is greater than 0. So when k is positive, what does that mean? That means the population is increasing exponentially. And then the question that you are going to ask me is, hey, should we approximate k to 3 or 4 decimal places? I want to say depends on the problem. Should we approximate k? When I solve exponential growth and decay, I do not recommend approximate k. So how about this? I am going to do a two problem. This one I am not going to approximate k, and then in the next problem I want to do an exponential decay as well. In that problem I will approximate k. So this one, let's just don't do it. So at this point, what do we have? We can update the model a little bit. So now is y equals to, the initial population is still unknown. We don't know what ka is, and then e to the kt. So that will be ln phi divided by 4 times t. And then let's find out what the initial population is. So I am going to take this down again. So when t is equals to 2, and then the population is equals to 100. So how about this? 100 equals to a times e to the ln phi divided by 4 and then times 2. And then we can solve for a, right? So a is equals to 100 divided by the entire e. So we have e ln phi divided by 4 and then times 2. That one we do have to approximate. So this one, since this is the number of bacteria, it doesn't make sense to have like half bacteria. I would just round this to the nearest integer. So this one is approximately equals to 45 bacteria. And then this is the initial population. Let's describe, put that in a different color. Initial population. And therefore, the model is the population model. You have y equals to 45 and then e to the kt. K is ln phi divided by 4 and then times t. And then we will be using this model to answer all the questions. So once again, the hardest part is when the model is not given. The hardest part is figuring out the model. After you figure out the model, everything will be extremely easy. Okay, so now let's back to the question. How many bacteria will be in the culture after 9 hours? So when t is equals to 9, let's show you how easy it is. So the y is equals to 45 and then times e to the ln phi divided by 4 times 9. So this one I did the math already. So that is 1682 bacteria. How about 20? Let's add another problem. So how about 20? How many bacteria are there after 20 hours? Should be a lot, right? So y is equals to 45. And then e to the ln phi divided by 4 times 20. So this one is approximately equals to 140,625 bacteria. What else can I ask? We have the population model. I give you the time, you give me the y. How about this? I give you the y, you give me the time. So how long does it take? I'm making up another problem. How long does it take to reach to 400 bacteria? So when t is equals to what? The population is equals to, how about this? Let's double that up. Initially was 45, right? So the double of 45 is 90. How about this? Initially we have 45. 2 hours later we have 200. So, wait, hold on. 2 hours later we have 100, right? Okay, how about this? 10 times. Because 2 hours is 190 bacteria. That will be less than 2 hours. Okay, let's do some other numbers. How about 450? 10 times. So how do we do that? So to do so, you have to let y equals to 450. That is equals to 45, and then e to the ln phi divided by 4 times t. This time you are solving for t. And then you divide both sides by 45, you have 10, right? And then that is equals to e to the ln phi divided by 4 times t. And then you ln both sides. So we ln the left hand side, we ln the right hand side, so that bring the exponent down. So we have ln10 equals to ln5, I wrote 4, ln5 divided by 4 times t, and then as a result, how about lne? Lne is equals to 1. So t is equals to ln10 divided by ln5, and then the whole thing divided by 4. So let's see what that equals to. I don't know yet. So let me do this in my calculator. We have ln5 divided by 4. I'm going to do ln5 divided by 4 first. And then I have the result in my calculator is approximately 0.402. And then I am not going to approximate that. I will just use ln divided by the answer. I will just use ln10, and then divided by the whole answer. So that one is approximately equals to, t is in hours, right? So t, am I right? So yep, t is in hours. How about this? Let's keep one decimal place. How about 5.7? It's 5.722706, 5.7 hours to make the population 10 times the initial population. All right, so once again, the summary is the hardest part is you have to set up the population model. After you set it up, you can answer all kinds of questions. They give you the t, you plug it in, you find what the population is, or the other way, they give you a population and then ask you to solve for t. All right, so that's it for this video. If you like the way I explain bacteria growth and exponential growth, give me a thumbs up. Give my channel a subscribe. Trust me, it is worthwhile coming back to watch for more math lesson. I will meet you all in the next video. Signing out.